Hi all, let's take a look at section 6.5, which is going to discuss complex numbers in polar form and De Moivre's theorem. Now, there's really a lot of different concepts packed into this section, but I think if you'll break it down component by component, each one's really not that bad. So now, if you look at my objectives here, you'll see what I mean about there being quite a bit built into it. The first thing that we'll do is we'll plot complex numbers in the complex plane. Very easy to do. It's just we're going to call the x-axis the real axis, and the y-axis is going to be our imaginary axis, and then it's pretty straightforward. We'll find the absolute value of a complex number. We will write complex numbers in polar form. We'll convert a complex number from polar to rectangular form. We'll find products of complex numbers in polar form. We will find quotients of complex numbers in polar form. And on the test, you would be given the two formulas for both the product and the quotient. It's not too bad of a formula, but nothing that you need to memorize. Similarly, I would give a formula for powers of complex numbers and a formula for roots of complex numbers. That's going to be the De Moivre's theorem once we try to find the roots of the complex numbers. Okay, so let's start off talking about the complex plane. Like I was talking about back on the previous page, I said whenever we graph an imaginary numbers, remember, are part of a complex number where we say the real component is the first term. So we can say any complex number, and usually we use the letter Z to represent a complex number. So we can say the complex number Z has the real component of A, and then the imaginary component plus BI, where B is the coefficient of the imaginary term. Now, in order to graph that, we would simply say, well, whatever value A is, we would go to on the real axis. And here in this picture, I'm assuming that A is obviously a positive value. I'm also assuming that B is positive because now you can see I've turned the y-axis into the imaginary axis, and I would say whatever number A is on the real axis, and then whatever number B is on the imaginary axis, I plot that just like I plot any ordered pair, and I could say this is my complex point. Z is equal to A plus BI in the complex plane. Oftentimes you'll draw a line from the origin out to that point, and that's going to be what's later called the modulus of this complex number, the distance from the origin to that point. Now, let's go ahead and look at an example of plotting a complex number. Let's say I ask you to plot Z is equal to 2 plus 3i. So again, every complex number is comprised of a real number component and imaginary number component. Clearly, the real number component here is 2. The imaginary component coefficient is 3. So we're just going to plot the ordered pair 2, 3, just as we would any ordered pair. You just say, well, the y value is going to become the imaginary value. Other than that, you just say x is 2, y is 3. You'd plot your point right here. My arrow is a little off there. It's supposed to be up here. But you would just say that's your point in the imaginary plane. You would, or sorry, I should say in the complex plane, you would need to label your real axis and your imaginary axis here. For the next example, I'm asking you to plot the complex number -3 minus 5i. So you see on the real axis, I went over to -3. On the imaginary axis, I went down to -5. You would plot your imaginary number -3, or sorry, I should say complex number. It has real and imaginary components. You would plot your complex number, Z is equal to -3 minus 5i, right here, it'd be in quadrant 3. And again, you could draw a line to it from the origin. I did that quite often in the homework problems. It doesn't have to be there, but it can be. Up next, it's asking us to plot the complex number, just Z is equal to -4. And you'd say, well, hey, this is easy because it doesn't have an imaginary component. This is just the real number, -4. So you say, well, on the real plane, I'll plot -4. So this is understood to be -4 plus 0i, since there is no imaginary component, just the ordered pair, -4, 0, and we'd say no problem. What if I give you a complex number that only has the imaginary component? Same idea, except now we would say, well, all I have to do is worry about the imaginary axis. It's not on the real axis. And the coefficient of the imaginary number is understood to be -1. So you're just going to plot 0, -1. My point would be right here at -1. And again, I could draw a line down to it with a point being at -1. Now, let's talk about the absolute value of complex numbers. So if we're looking at complex numbers out in the complex plane, then the absolute value is just the distance from the origin out to that point. And we can quickly and easily see here, well, that distance, it's just going to be the hypotenuse of a triangle, in which the horizontal component is just your real value, and the vertical component is your imaginary coefficient. So you'd say, well, then the absolute value of any complex number is just going to be the square root of a squared plus b squared, where a and b, a is your real number, b is the coefficient of your imaginary number in your complex term. So we'll always be able to draw it out and just say, well, it's just the hypotenuse, it's the distance from the origin to your point, which is always going to be the square root of the horizontal component squared plus the vertical component squared. Or you could say the square root of the real component squared plus the coefficient of the imaginary component squared. Now, when we look at an example of that, pretty straightforward. If I say, I want you to find the absolute value of the complex number 5 plus 12i, well, the absolute value of 5 plus 12i is going to be the square root of the real component squared, 5 squared, plus the coefficient of the imaginary component squared, 12 squared. 5 squared plus 12 squared, that's 25 plus 144, gives us 169 inside the square root. We're going to get a 13 there. So we can literally say the absolute value of the complex number 5 plus 12i is 13. Now, if I'm asking you to determine the absolute value of 2 minus 3i, same idea. You'd say, well, it's just the square root of the real number component squared plus the coefficient of the imaginary number coefficient squared. And you'd say, well, in this case, it's going to be 2 squared plus -3 squared. Doesn't matter whether you put the negative in there or not. Of course, since it's being squared, you're just going to get 4 plus 9. That's 13. Our absolute value of 2 minus 3i is simply the square root of 13. Now, if I have polar form of a complex number, the polar form is going to be in the expression z is equal to r, where r is the distance from the origin. It's the absolute value we was talking about in the last one. You could say it's the same thing as the absolute value of your complex number. It gives the distance from the origin to the point times the cosine of theta plus I sine of theta, where theta is just the angular distance of where your point is in reference to the initial x-axis. So now, if I try to look at how I'm going to do this, I'll go in and say, well, that complex number, which is always, it's going to change. Now, the original form where we have z is equal to a plus bi, that's the rectangular form. We're trying to find the complex form. Here, I forgot to put the b before the I there. If we're trying to form that rectangular form to the polar form, we can always just say, well, the horizontal component, which is going to be the a value in our complex number, that's always going to be the r cosine theta. The vertical component, that's the b, that's the coefficient of the imaginary number. It's always going to be r sine theta. And then we can say the angle is always going to be the tangent of theta is going to be the imaginary coefficient b divided by the real number component a. Whenever you draw it out, it becomes obvious because you're just saying the tangent of theta. Oh, it's the vertical divided by the horizontal, the opposite over the adjacent. Now, this value of r, I think I referred to this earlier. It's called the modulus. The modulus is simply the distance the point in the complex plane is from the origin. If you have more than one r value, call it moduli for the plural. You don't need to know the vocabulary. I just need to know that you can work the problems. So looking at a problem here, if I ask you to plot the complex number in the complex plane, then write it in polar form. Now, the reason I ask you to plot it in the plane is because it becomes almost a necessity. It's very, very difficult to do these without understanding where the complex number is at. So if I'm looking at this here, I've got my little arrow at where the point would be. The complex number, the real number component is -1. So I go to -1 on the x-axis. And then the imaginary number is -I on the root of 3. Well, I know that the root of 3 is like 1.732. So I'm going to the left 1. I'm going down about 1.732 units. So you can see that's why my little arrow there, it's not quite all the way down to -2. It's supposed to be pointing to the ordered pair -1, comma, -1.732. Now, whenever I have that point in there, then I'm thinking, okay, well, then I know that the theta value, it's going to be the angle that it would take to rotate from the original x-axis to where this point is. And again, it might help if you draw a line from the origin to that so you can see where you're rotating around to. I know my theta value, it's going to be an angle in quadrant 3, and it's going to be going down more than it's moving to the left. The only angle in quadrant 3 that I'm supposed to know that moves down more than it moves to the left, hey, 4 pi over 3. If it were 5 pi over 4, the horizontal and vertical change would be the same. The vertical's moving down more than the horizontal's moving to the left. So I can say that has to be at 4 pi over 3. That's the only angle in that quadrant where that would happen. Now, I'm pretty sure I know the angle just from looking at the graphed point here. But let's go ahead and find the r value. Well, the r value is very straightforward. It's just going to be the square root of the a value squared plus the b value squared. Notice I do that on the next page. R is going to equal the square root of a squared plus b squared. That's just -1 squared plus the negative root of 3 squared. I'm getting 1 plus 3. Hey, square root of 4 is 2. So I know my r value is 2. Now, showing the tangent formula out, you'd say, well, the tangent would equal b over a. That's going to be the negative root of 3 divided by -1. It's going to give me the square root of 3. Now, here's where it gets frustrating. Students will take that square root of 3, put it into their calculator, and in degree mode, it's going to give them 60 degrees. In radian mode, they might be able to figure out it's pi over 3. Because your calculator is only capable of, whenever you're saying theta is the inverse tangent of the root of 3, remember, it's only capable of giving you an angle in quadrant 4 or quadrant 1. It's completely incapable of giving you answers in quadrant 2 and 3. So we have to use our knowledge of the unit circle and say, well, all right, if it's giving me that theta is pi over 3 in quadrant 1, I need to find the angle that has pi over 3 as a reference angle to it in quadrant 3 down here. So you just say, well, it's going to be pi plus pi over 3. That's your 4 pi over 3. And if you have any doubt, you could go to your calculator and say the tangent of 4 pi over 3, and you're going to get 1.732, which is the square root of 3. Now, I know the angle, I know the r value, I can put it in polar form. It's very easy at this point. Polar form is just z is equal to r times the group cosine of theta plus I sine of theta. Boom. Notice on the next page, z is equal to r times cosine of theta plus I sine of theta. I know r, I know theta, I know the polar form. It's as simple as just plugging it in. Once you find your r value, once you find your theta, you're going to say the polar form of this complex number is z is equal to 2 times the cosine of 4 pi over 3 plus I sine of 4 pi over 3. Now, if for any reason you thought that you might be wrong, you could easily check yourself. You could say, well, this 2 should be able to distribute back into here. 2 times the cosine of 4 pi over 3 will give you the -1. 2 times the sine of 4 pi over 3 will give you the negative root of 3. That's multiplying the I term there. So you'd say, yeah, that would be perfect. You could easily check yourself on these problems. It's very easy to go from polar form back to rectangular form by just distributing and multiplying. Now, if we're multiplying complex numbers, most complex, well, all complex numbers have a modulus, R1, that's just giving the point's distance from the origin. Now, the reason I started to say most instead of all is sometimes you won't see it, but what if you don't see it? Then it's implied to be 1. So if you just see cosine theta plus I sine theta, it's because the R value is 1 in that case. But for anything else, you're going to see a coefficient out in front of the cosine of theta plus I sine of theta. So let's say you have 2 complex numbers and you're trying to find their product. It's so much easier to multiply when you have them in polar form. So the first step, if for example you're giving them in rectangular form, the first step would be to get them in polar form. And then once they're in polar form, you can just say, well, then the product of those two, you just multiply the two R values. So you'd say R1 times R2, and then it's going to be the cosine, the sum of the angles, plus I sine the sum of the angles. So now let's look at an example of that. Let's say I give you the polar numbers Z1, which is equal to a modulus of 6 times cosine 40 plus I sine 40, and Z2 has an R value of 5 times the group cosine 20 plus I sine 20. Well, I know their product is just going to have the product of the R values times the cosine, the sum of the angles, plus I sine the sum of the angles. I'll get 6 times 5, the product of the R values. It'll be cosine of 40 plus 20, and obviously I sine of 40 plus 20. My final answer, you'll get 6 times 5 is 30, and then you'll have cosine of 60 plus I sine of 60. That would be your absolute final answer in polar form. Now, what if they said we want the answer back in rectangular form? If they want it in rectangular form, you would just say, well, distribute this 30 through there, and your real number component would be 30 times the cosine of 60. That would be 30 times 1/2. Your real number component would be 15, and then you'd say plus 30 times the sine of 60 times I. 30 times the sine of 60, that'd be 30 times the square root of 3 over 2. You would have 15 plus 15 on the root of 3 times I, if you put this back in rectangular form. But in this case, it said leave the answer in polar form, so what I have is good. I was just doing a hypothetical there if I wanted it in rectangular form. Now, what if you want to divide complex numbers? It's so much easier, yet again, if you'll put them in polar form first. So in polar form, I know that my modulus is going to be on the outside, and I'll have the cosine of the angles plus I sine of the angles on the inside. So then when I say, well, Z1 divided by Z2, it's just their respective R values divided. So I'd say R1 divided by R2 times the cosine of the difference of the angles, and then plus I sine the difference of the angles. One thing to keep in mind, whenever you have an answer in polar form, the cosine of the angle and the sine of the angle will always be the exact same angle in there. So that's one thing to keep in mind. They will never have different angles in there. In this case, we're just saying the difference of the two angles. Now, whenever I'm trying to figure that out for a specific problem, I could say, well, what if Z1 was 50 cosine 4 pi over 3 plus I sine of 4 pi over 3? Z2 is going to be 5 times the cosine of pi over 3 plus I sine of pi over 3. Well, I'm using my formula, and I would say, well, all right, Z1 divided by Z2, you would take this R value, divide it by this R value, 50 divided by 5, and then your cosine is going to be of the angle this angle minus this angle. So you say 4 pi over 3 minus pi over 3. Same thing for the I sine 4 pi over 3 minus pi over 3. Whenever you divide your R values, of course, you get a 10 for the modulus out front. And then you'd have 4 pi over 3 minus 1 pi over 3 is 3 pi over 3, which is just pi. You're going to have 10 times the cosine of pi plus I sine of pi. Now, this would be my final answer in polar form. Again, what if hypothetically you wanted an answer in rectangular form? Well, one good thing about this one in rectangular form, you could see there's not going to be an imaginary component because the sine of pi is 0. Cosine of pi is -1. You'd have 10 times the -1. The quotient of z1 divided by z2 is just going to be -10. So that would simplify to be a real number component of -10 in rectangular form. But again, you would leave it like that if you wanted your answer in polar form. Now, powers of complex numbers. Again, all of these formulas, they're not that hard, and they would be pretty easy to memorize, but I would provide them on a test. So this is just saying, if you want the nth power of any complex number, then again, it's much easier if it'll be in polar form to begin with, and then the nth power of that polar form, you just take the R value to the nth power, and then you're going to multiply that nth power times each of your angles. So it becomes the cosine of n theta and the sine of n theta. Let's look at an example of that. Let's say we're trying to raise the complex number in polar form. 2 times the group cosine of 30 degrees plus I sine of 30 degrees to the 5th power. So you'd say, okay, pretty straightforward. I take the 2 to the 5th power portion, and then I would have the cosine of 5 times 30 for my first angle plus I sine of 5 times 30, n times theta. And so then I could say, well, all right, 2 to the 5th power is 32. I would have the cosine of 150 plus I sine of 150. Now, unlike the previous two examples where I left the answer in polar form, this time I ask you to write the answer in rectangular form. Had I said leave the answer in polar form, this right here would be my final answer. For the rectangular form, I just have to think about what's the cosine of 150 and the sine of 150. Well, at 150 degrees, that's 30 degrees short of pi, or 180 degrees. I know at that value, my sine is 1/2, my cosine is the -square root of 3 over 2. So you could see I plugged in cosine of 150 is the -square root of 3 over 2. My sine of 150 is 1/2. Then at that point, I would just distribute the 32 through, and I would say the real number component is going to be -16 on the root of 3. And then the imaginary component is going to be plus 16i. That would form your complex number in rectangular coordinate system. Now, De Moivre's theorem. De Moivre's theorem is just telling us how we're going to take the nth root of a complex number. So we've already talked about how to find the nth power. The nth power, much easier because there's one distinct answer. You just say it's the R value to the n times the cosine n times theta plus I sine n times theta. Very straightforward. Well, De Moivre's theorem is saying, well, the roots aren't that nice. And in fact, the smaller the root, the greater the index on the root, the more answers you have. We're going to have n distinct complex nth roots. So if I say, hey, the square root, it's going to have 2 answers. The cube root, it's going to have 3 answers. The 4th root, 4 answers. The 5th root, 5 answers. The 6th root, 6 answers, and so forth. Now, would I ever ask you to find more than the complex 4th roots of any complex number in polar form? Absolutely not. That's what I did here in my examples, and it's pretty long in and of itself. More than likely, it'd be a square root or a cube root where there's 2 answers or 3 answers. Now, our formula for that And it just depends whether you're going to put it in terms of degrees or radians. Doesn't matter. It's the same formula. This formula, the only thing that's different is you see where I put the 2 pi here, I put 360 degrees here. I sort of prefer to deal with radians most of the time, but it doesn't matter. What you'll say is that z sub k, where k is equal to 0 up to n minus 1. So, for example, if it's the cube root, then n is 3. K is going to be 0, 1, and 2. You're going to have 3 answers for k, 0, 1, and 2. If it's the 7th root, you're going to have you're going to have 7 solutions, but you're going to have k equals the values 0 up to 6. It's always up to n minus 1. Now, so if I have z sub k is equal to the nth root of your radial, of your r value, your modulus, the distance from the origin to your point, times the cosine of theta plus 2 pi k over n. And again, remember, k is going to go from 0 up to n minus 1, whatever your nth root is, and then plus I sine of theta plus 2 pi k over n. Now, let's look at an example of this, because otherwise this looks pretty confusing. So let's say I ask you to find all complex fourth roots. And I said on the previous page, I would never ask you to find more than the fourth roots, just because there's going to be 4 answers to this problem. If it were the third roots, there would be 3 answers. Square roots, only 2 answers. So I need the complex fourth roots. And so you'd say, well, all right, here's how I go about doing that. So first of all, if I think about the angle in the problem, that's my value of theta. So you'd say, well, theta is going to be 60 degrees. And then I can say there's going to be exactly 4 solutions. The first solution occurs when k is 0. So I'd say, all right, my formula is asking me to take the nth root of the r value. Well, the 4th root of 16 it's just going to be 2. I could have went ahead and put a 2 there, but I wanted you to see I'm taking the 4th root of 16 and then times the group. I'll have the cosine. Theta is just your initial angle that you had within here, so it's in degrees. And then you'll say plus 360 degrees times 0. That's the value of k, all divided by the n value. Well, it's the 4th root, so that's 4 down there. And then, of course, plus I sine of that exact same angle. Now, simplify your angle. You're just going to have 60 divided by 4 here. 60 divided by 4 is going to give you an angle of 15. So when we simplify this, you can see that your first answer for the 4th root of 16 cosine 60 plus I sine 60 is 2 times the cosine of 15 plus I sine of 15. Now let's get to the second solution when k is 1. When k is 1, you're going to do the same thing to the outside. Sometimes students make a mistake and they want to take the different numbers. They say, oh, I need to take the first root of that out there. No, that's always the nth root, which in this problem, it's always 4. The only thing you're going to change for the z sub k is the value of k right here inside your problem. In the previous problem, it was z sub 0. Z sub k is 0, so you put a 0 in there. Now, the only thing different in this is you can put a 1 in there for z sub 1. And so you'll say, well, the outside's still going to be a 2. It's the angles that change. This time you have 60 plus 360, be 420. 420 divided by 4, that's going to reduce down to 105. So your second 4th root of this complex number is going to be 2 times the group cosine of 105 plus I sine of 105. And so we can say, okay, 2 solutions down, 2 to go. The next one's going to be z sub 2. What's going to be the difference between z sub 1 and z sub 2? The only difference on the next page is wherever you see a 1 right here, I'll have a 2 on the next page. That's it. Boom. You can see z sub 2 It's going to be the 4th root of 16 times the cosine of 60. Again, that's just your original angle you had, plus 360 times 2 over 4. Well, 360 times 2 is 720. 720 plus 60 is 780. 780 divided by 4, it's going to give you 195. And that's going to be the same angle in both of your trig functions, always is the same angle. And so we can see that our third solution occurs when k is 2, and you're going to have 2 times the group cosine 195 plus the sine of 195. Move on to my last solution. You could say, well, not surprisingly, the only difference between z sub 2 and z sub 3 is you change the value of k within your angle. This time your angle is going to be the cosine of 60 plus 360 times 3. That's going to be 1080 plus 60. 1080 plus 60 is 1140. You take that 1140 divide by 4, you're going to get angles of 285 for each of those. Now, each one of these solutions are a complex 4th root of this number. So we can say, well, that complex number, 16 times the group cosine of 60 degrees plus I sine of 60 degrees in polar form, all 4 of these are solutions. So we say the complex 4th roots are 2 times the cosine of 15 plus I sine of 15, 2 times the cosine of 105 plus I sine of 105. And then really once you find the second one, you can kind of see what's going to happen for the other two. You say, well, all I did was I added 90 degrees to get from this one to this one. So I know I'm going to add 90 degrees to get from this one to this one. And I'm going to add 90 degrees to get from this one to this one. And so you could say all 4 of those together are going to be your complex 4th roots. That is the de Moivre's theorem. And again, de Moivre's theorem and all of these other formulas I would give you on the test. You just have to be comfortable in using them as I've done here in this example. All right, guys, that'll do it for section 6.5. Please let me know if you have any questions. I'll be glad to help.